In this video, we'll talk about translational and rotational acceleration of a liquid. So what we're going to look at, we're going to look at the case where we have a liquid inside of a tank and the tank is accelerating. How does the liquid levels change due to that acceleration? So to start, let's imagine we have a tank that has some water in it and it's accelerating with a constant acceleration to the right. Obviously, what's going to happen is the level in the tank is going to change. It's going to get less than the right end, and it's going to increase on the left end. The question is how much? How much so? Well, the book goes through a detailed proof, and it shows that this angle, this theta angle, is related to a ratio of the acceleration to the acceleration due to gravity. And so you can find this angle, so you can find exactly how much the height changes on each end. It's symmetrical, so if it goes up by d here, it goes down by d here. So once you know these heights, you can simply use the fact that the pressure equals the gamma times h to find the pressure at any point in the liquid. Now, if the container has a closed lid, then what's going to happen is the liquid is going to build up at the top. It can't get out. The level is going to shift, but it can't really get out up here. So one way to work this is to imagine that you have an imaginary surface. If the lid wasn't here, how high would the liquid go? And then once we determine that based on the formula, we can apply the pressure equals gamma times h to find any pressure we want. So for example, we want to know what the pressure is here at A. It's just gamma times HA. The pressure at C is equal gamma times HC, which is the height all the way to the top. So again, it's exactly the same. Yeah, this is an imaginary liquid surface, but you can determine theta. Once you know theta, if you know, for example, this height from here to there, or the distance from here to there, you can find the distance from here to there, HA, by using this formula here, by simply setting up ratios. Now let's imagine for a moment that the liquid is accelerating vertically. Well, the book goes through and shows that what happens is that the pressure, if it's accelerating upward, the pressure changes at depth h is given by gamma h times the ratio of the acceleration of the container to the acceleration due to gravity. If it accelerates downward, then the pressure is decreased by this amount. So here you can set up, a simple formula that the pressure at any point h is going to change by an amount equal to this. You just have to remember that this is either plus or minus depending on if it's accelerating downward or upward. So it's not always plus. Sometimes it's a minus if it's accelerating downward. So let's look at example 2-20. So a tank of gasoline is moving to the right at 4 meters per second squared. He gives us the dimensions of the tank, and he wants us to find the pressure at A, B, C, and D. He tells us this, assume it's gasoline that has a density of 726 kilograms per cubic meter. So here we can use the formula tangent theta. So tangent theta equals h over 8 meters. And that equals the acceleration of the truck divided by g. So the only unknown here is h. So we can find h is 3.262 meters. And now we know that we can find the different pressures because we can just use pressure equals gamma times 8. So in other words, the pressure at A, so the height here is 0, so the pressure here is 0. The pressure at B is simply gamma times HB, so this is gamma, the density times G times the height here, 3.262. The pressure at C, you just add on 2 meters, so it's 5.262 meters. That's the pressure at C, and the pressure at D here is the distance from HD, which is 2 meters. So same height here as it is there. So the pressure here is 14.2 kilopascals. Now, the last section of this chapter talks about the steady rotation of a liquid. So let's put a liquid in a cylindrical container. Let's say it rotates at a constant angular velocity omega. So what happens is the level of the liquid is going to change. It's going to establish this parabolic kind of shape where it rises a certain height here and falls a certain height in the center. So when it does set up this parabolid, the equation of the surface can be determined or can be shown to equal to this formula here. H is equal to omega squared over 2g times r squared. So r here is the distance from the center. So so if you want to, so the height, for example, from here to there, that's we're talking about the height difference from where the bottom of the level is, so the bottom of the level. So here's h. Well, given r, you can find the h. So if you want to find the total height from say here to up the top, you would simply substitute r is equal to big R. Then once you know those heights, you can simply use the pressure equals gamma times h to find the pressures. So he works an example 2.22. He's got a cylindrical drum full of oil. Oil has a density of 1.71 slugs per cubic feet, and it's rotating at 16 radians per second. He shows us the dimensions of the tank. So before finding the pressure, we must define the shape of the oil surface. So here shows the shape of the drum before rotating. As it starts rotating, the liquid is going to disperse and move up the sides of the cylinder. So it turns out it moves into a shape of a parabolid. So you still have the same liquid, but instead of being a cylinder, that volume is now distributed over a parabolid shape. So what's the volume difference between a cylinder and a parabolid? It's exactly half. So the volume of a cylinder is pi r squared times the height. That's going to be the height here, the 1 foot. So you're gonna move some of this liquid up into that shape, exactly half of it. So 1/2 pi r squared h. So you don't know r or h, but you can set up a relationship here, solve for r squared h. So you need another equation to be able to solve this. So we also know the fact that of how high it's going to rise. It's given by that previous formula. H equals omega squared over 2g times r squared. So we know omega, we know g, so we can again find another relationship between h and r. So we have two equations, two unknowns, and so we can solve. So here's our equation 1 and equation 2 from the previous slide. We can take the h here, plug it up in here, solve for r. And then we can also, once we have r, we can plug it back in here and solve for h. So if we didn't have the lid on, how high would the liquid rise? Well, it would rise a distance h prime is equal to omega squared over 2g. So what r value would we plug in? We plug when small r is equal to the total r, which is 1.25 feet. Remember, it's half of the total diameter. So that turns out it's 6.211 feet. So now we can determine the pressures, because the pressure at A here is going to be gamma times HA. So how high is HA? Well, it's this distance here. So it's 4 feet. This distance here, 4 feet, minus the 3.525 feet. So we know this distance, we know that distance. We can subtract them and get HA, the height from here to there. So it turns out it's 0.182 psi. Now, if we want to find the pressure at B, we have to find the height of this total liquid here from here to there. So we know gamma is the same. So we have we know the distance from we can just kind of sort of add it up. So we got 6.211 feet. That's that distance from here to there. But we need this little bit here. So what's that equal to? That's equal to the 4 feet minus the 3.125 feet. So it's the distance from here to there plus the distance from here to there. So 4 feet minus 3.525 feet gives us this distance from the bottom to the top here. And then we just got to add 6.211 feet to it. And then we got to convert from feet to inches to get it in pounds per square inch. All right, so that's the end of this lecture and the end of chapter 2. And, we'll work some problems and get started on some problems.